Okay, everybody. In this video, we're going to introduce the concept of energy. And in order to talk about energy, we're going to try to relate energy to two common everyday terms that people use to describe something related to energy. The first of them we're going to refer to as effort, and the second will be effect. There's a table on the whiteboard that you can see that has three different amounts of effort that are expended, and we're meant to compare them. So the question is, if you applied a force of 8 newtons over a distance of 3 meters, or a force of 16 newtons over the same 3 meters, or finally, in scenario C, a force of 8 newtons over 6 meters, which of these would be the greatest effort? And by that we mean which would be more difficult to accomplish, which would be worth more money if you were being paid to do these as a job, which might cause you to sweat more, something like that. So if you had enough time to look at the three comparisons here, A, B, and C, maybe by now you've decided for effort, I think A is definitely less than B. It seems that A is also definitely less than C. And maybe we can't be certain about how we could compare B and C. I'm just going to say B has a relation to C that we don't know yet. No matter how we think about it, it does make sense to agree that effort should be a function of or depend on force and distance. Similarly, on the bottom of the whiteboard, you can see a table about effect. By effect, we mean maybe something that would do more damage than something else. Maybe what would cause a bigger hospital bill than something else if it happened to you. And the effect here seems to depend on mass and velocity. So again, we'll make a comparison. If a mass of 10 units, probably kilograms, at a velocity of 20 meters per second, if we were using standard units, that's scenario A. If that object ran into you or a wall or did some damage to something, would it have a greater effect than option B or option C? If we compare A and B, it does make sense that B should have a greater effect than A. Because if you get hit by objects that are going the same speed as each other, well, one of the objects has twice the mass, then it will definitely do more damage to you. We can also compare A and C and say A is without a doubt less damage or less of an effect if it collides with something than C is, because they have the same mass, but C is going twice as fast. Again, you might think that they'd be equal, but we can't say for certain yet whether whether B or C is a larger effect if it collides with something or gives its energy, use the word, to some other object. Either way, the effect that an object has on another object when it collides with it seems to depend on mass and velocity. What we'd like to do is find a relationship between effort and effect. Perhaps by looking closer in a different way at some physical situations that we've looked at before in class,
we can find a mathematical relationship between force and distance or mass and velocity. So to do that, we're going to make up a definition. If it works, if it tells us something useful, we'll stick with it. If not, we might dump it. Here's our definition. We're going to define effort as follows. We're going to say W for work equals force times distance. This is by definition. If it leads us to any useful conclusions, we'll keep it. So here is our scenario that we're going to use to try to determine a relationship between effort and effect. This is a mathematical relationship, so you should expect to have to do some physics here. I'm going to move to the whiteboard. Okay, here we assume we have an object with mass m that is pushed with a force F from rest, so VO equals 0, over a distance d. And the question is, how fast is it moving once it's traveled that distance? In other words, what's the final velocity of this mass? It should remind you instantly of your kinematic stuff. You could say VO equals 0. You could say V is I don't know what. So the acceleration is we'll see. And the distance covered is d. And if we knew what the acceleration was in terms of the other unknowns, or knowns, as they might be, then we could solve this. We don't know the acceleration until we think about the force. The force we've been given is F. The mass is m. And by Newton's second law, the acceleration must be the force divided by the mass. So, using our old kinematics equation, we can reach this conclusion. V squared equals 2 times F over m times the distance. And if we look at this not even particularly closely, we can see that force and distance, which were related to effort, are together in this equation. We can also see that mass and velocity could be put together in this equation, and those are what are related to effect. So let's do that. If we have V squared equals 2 FD over m, then we have FD, if we keep them together, equals mv squared, and then divided by 2 on both sides. So we could write 1/2 mv squared. This is a mathematical relationship between our two quantities. This is what we've now defined to be effort. And then the conclusion is that the effect variables, mass and velocity, are related to the amount of effort that was put in. Here's what we conclude from this work. If we define work to be force times distance, we conclude the effect is 1/2 mv squared. This is an effect of motion.
what we're saying is if you push with a force F on an object at distance d, then its mass will acquire a velocity that is given by this relationship, that Fd is equal to half mv squared. This effect of motion is a kinetic effect, kinetic meaning moving. So we can now define this motion effect as being kinetic energy is 1/2 mv squared. That is, if work is force times distance, then kinetic energy is 1/2 mv squared, is what results from that effort. The effort F times d produces the effect 1/2 mv squared, or work produces kinetic energy. Just to be sure that this is true, we should compare this new way of relating forces, displacements, masses, and velocities to our old ways, which involved forces. So I'd like to make up and do a problem in both the old way and the new way next. Here's our situation. Suppose we have a 3 kilogram mass pushed by a 12 Newton force over a distance of 8 meters. How fast will the mass be moving at the end of the push? In other words, what's the final velocity? If you got this problem in February, you would do the following. Here's our old way to handle this situation. We would say a force of 12 newtons acts on a mass of 3 kilograms and accelerates it by Newton's second law. The acceleration is 4 meters per second squared. We then say the final velocity is unknown. The initial velocity is 0. The acceleration is 4 meters per second squared. And the distance is 8 meters. By our third kinematics equation, we could find the final velocity. V squared is 64, means V is 8 meters per second. The true test of our new idea is, does it give the same answer for the final velocity? So here's our new idea. Our new idea says that when you do work, or if you make an effort that can be quantified now as a force times a distance, an effect will be produced, and that effect will be the quantity 1/2 mv squared. So let's try it. If you pushed with a force of 12 newtons for a distance of 8 meters, how much work would you have done? By our definition, work is force times distance. So the work done here is 12 times 8. 12 times 8 is 96. And at this point, it's probably appropriate to talk about what the units are, because there are units of measure for effort or effect, and they are joules, named after James Joule, who did a lot of experiments in the 1800s with his horses related to their energy and power output. The amount of work done here is 96 joules. Capital J is the abbreviation for joules. And we have to use standard units in order to work with energy, which means that it's only joules if it had come from things like newtons, kilograms, meters, seconds, and things like that. This is not an answer to what the speed is. We're still looking for this 8 meters a second to come out of our calculations. But what we're now ready to say is that the effort that was put in, which was 96 joules, is apparently, by our proof on the board, equal to the effect that is produced. In this case, it's a kinetic effect, so that the block in the picture above would end up with a kinetic energy of the same 96 joules. And you can see the unknown now is the velocity. We've got 96 equals 3/2 of v squared. 2/3 of 96 gives us v squared. And 2/3 of 96 is 64. So v comes out by our new method to also be 8 meters per second. In other words, we can use old or new thinking. We could talk about forces and kinematics, or our new concept, which is energy, in order to calculate things that we've been doing all school year, pretty much. There's one last detail to add for today's lesson, which is an introduction of energy as a whole, but specifically it's an introduction to work, kinetic energy, and a third type of energy. For this, we have to imagine that it takes an effort in order to lift things. Assuming that you pick up, say, 1 kilogram, test out my sketching ability here. This person has picked up from the ground to a height of 2 meters a 1 kilogram block. Before, the block was on the ground and it ended up 2 meters above the ground. I think anyone who's done it would agree that this would require some amount of effort. The effort that it would require, as we said before, effort, we're now ready to equate to this physical quantity called work, which we have defined to be force times distance. The effort here would be the amount of work done in lifting it from the floor to the height, which I've said was 2 meters off the floor. So the distance that it was raised is 2 meters. The force that was applied in order to lift it is the weight of the 1 kilogram. And you'll remember from before that the weight of any object is really its force due to gravity, which is its mass times the acceleration due to gravity. Or here, we should remember that this is a 10 Newton weight. If you lift or push with a force of 10 newtons over a distance of 2 meters, we've now said that the work you've done should be 20 of our new energy units, which are again called joules. Once this mass has been raised to this height, we'd have to admit that it doesn't have any kinetic energy. Question is, when you raise a kilogram 2 meters off the ground, how can you get the energy back? How is it possible to get the energy again? If you said you should drop it, you're right. That's exactly how you get back the energy. The question is, do we get back all of the energy, all 20 joules of it, or do we get some smaller amount? We can analyze the situation using, again, our old methods. Here's some old physics to help us decide whether we get all of the 20 joules back when we drop this weight to the floor. If we dropped it from rest at a height of 2 meters above the ground, and it accelerated down towards the ground at 10 meters a second squared, how fast would it end up going by the time it got to the floor? Here again is some old physics that we've all done our fair share of this year. V squared comes out 40, which means that V is the square root of 40, whatever that is. The question is, if we put in 20 joules of effort to raise the 1 kilogram up to this height of 2 meters, if we release the 1 kilogram and it falls to the floor, eventually reaching this speed of the square root of 40 right before it hits the ground, how much of an effect will it have on the ground? In other words, what is its kinetic energy when it reaches that point? We now have that kinetic energy is 1/2 mv squared. And in this case, the kinetic energy would be 1/2 the mass, which is 1 kilogram, times the speed, square root of 40, squared. We end up with half of 40, which is 20 joules. What this says is, if you put in an effort of 20 joules to raise this 1 kilogram to the 2 meter height above your head, when you let go of it, it ends up producing an effect on the ground that is just as energetic. It puts as much energy into the ground as the person put into it by lifting it for 2 meters. Besides seeing that we get all of the energy back upon releasing the mass, we also have to admit that when the mass is at this highest height, it has something. The work was done, the effort was made to lift it from the floor to where it is when it's in this person's hand. But before it's released, it doesn't have any kinetic energy, meaning it's not moving. And it doesn't have any effort being currently made to it. So where does this 20 joules of kinetic energy come from? If we were able to be in school, this is the time when I would hold some heavy weight, some distance, short distance above a student's head. Perhaps someone who had zoned out some time ago. And I would ask them if they were anxious about the weight being in one position versus another. If I hold a bowling ball 2 feet above a student's head, they have reason to be worried, not because of what's currently happening, but because of what could happen. If you see the possibility of energy, like this person who is holding this weight 2 meters above the ground, we need to be able to describe or have an equation or a formula for the possibility or potential of energy being released. In this case above, we've actually already determined a way to find potential energy, at least due to gravity. If we say that the work that is done in lifting this 1 kilogram mass was a result of a force times the distance, and if in this case we're talking about the force being the force of gravity, and the distance being the height that it was raised from the floor, then we're ready to say that there is a gravitational potential energy by this block of weight being in this position that is equal to the force of gravity, or its weight, times its height. Or the way that we really refer to it, gravitational potential energy is its mass times the acceleration due to gravity times the height. Here is our third and for today final form of energy that we need to add to our collection. In summary, we've now established that if we define work to be force times distance, doing work on an object can produce one of two effects to this point. One of those effects would be to give the object kinetic energy, meaning that it is now a mass with a velocity. And we derived an expression for kinetic energy that is 1/2 mv squared. Another expression or effect of applying an effort to an object would be to change its position. We might do work in order to give an object gravitational potential energy. Which is an energy that is related to its position in a gravitational field. All of these units must be standard. This means if you have a force, you have to write it in newtons. If you have a distance, it has to be meters. If you have a mass, it's kilograms. A velocity has to be in meters per second. An acceleration due to gravity has to be meters per second squared. And a height would have to be in meters as well. That's it for today. At this point, you should do some independent practice.